So this video introduces absolute convergence and the corresponding absolute convergence test. So suppose that you have a series that contains an infinite number of positive and negative terms, and it's not an alternating series. Well, now in this case, we still have a few techniques, and they're still pretty powerful, but they need an explanation why they work. The first one basically says, just take the series that you have and pretend that all the terms instead are being added, and consider whether that series converges or not. So let's suppose that we have a series whose absolute value of the terms converges. This is basically the original series, but where I take every term and just make sure it's positive and add them up instead. And consider the new series where you take the old terms plus the absolute value of that same term. Notice that a sub n plus the absolute value of a sub n, that thing is either equal to 2 times the term, a sub n, or it's actually 0 because they might be opposites. Either way, you have that a sub n plus the absolute value of a sub n is non-negative and bounded above by 2 times the absolute value of a sub n. So that means that the series of a sub n plus the absolute value of a sub n, that thing converges by direct comparison to the series of 2 times the absolute value of the sequence a sub n. But that would then mean, if you remember, that since the difference of convergent series converges, then if you take these two series and subtract them and then add them together, the new series, which is the original series as n goes from 1 to infinity, that series also converges. So that gives you this test, that if you take the series as n goes from 1 to infinity of the absolute value of the terms, so that you're always adding them all together instead of subtracting them sometimes, then if that series converges, then the original series converges. This is called the absolute convergence test. Now, for example, what if I wanted to know, does the series of the cosine of n over n cubed as n goes from 1 to infinity, does that converge or not? Now, it's not an alternating series, because if you look at the cosine of 1 and then the cosine of 2, cosine of 1 is positive, cosine of 2 would be negative, but the cosine of 3 is actually also negative, so it doesn't alternate sign. But instead, just consider what you get when you take the series as n goes from 1 to infinity of the absolute value of the terms in that original series. Notice that the absolute value of the cosine of n all over n cubed is always at most 1 over n cubed and is always at least 0. Also, the series as n goes from 1 to infinity of 1 over n cubed, this thing converges by the P series test. So that means that the series as n goes from 1 to infinity of the absolute value of the cosine of n over n cubed, that thing converges by direct comparison and direct comparison with this series right here, because each of these terms are less than that term. Since this series term converges, then this guy converges. And therefore, by the test I just gave you, consequently, so then the series as n goes from 1 to infinity of the cosine of n over n cubed, that thing also converges. And that's it. That's how you show that that series converges. Now, if you have that the series of the absolute value of the terms converges, well, that means the original series converges. But it is possible, though, that the series of the absolute value of the terms doesn't converge, and yet the original series does. So now we have two different types of convergence. We'll call it absolute convergence and conditional convergence. Absolute convergence means that the series of the absolute value of the terms, that converges, because then the original series converges anyway also. The other one is that the original series converges, but the series of the absolute values doesn't. Now, you might wonder then, why do we care? Like, what's the difference between absolute convergence and conditional convergence? Well, there's actually a bunch of algebraic properties that are true only for absolutely convergent series. Now, the big one that's important for us, and we're not proving it, we're just going to use it, is that if you reorder the terms in a series, you technically get a different series. Remember, the series is defined specifically as you add the terms left to right in the order that you're given to you. So, if you take an absolutely convergent series and just reorder the terms any way you like, you actually always get the same sum. But a conditional convergence series, if you change the order of the summation, you actually can get different answers. And in fact, what's really neat, it's possible to show that for a conditional convergence series, you often can make it add to be anything you want at all. So the order that the summation is done for a conditionally convergent series is very important. You must do it exactly left to right, or you might get a different answer. So let's go ahead and look at this particular series. I'd like to know what kind of convergence it has, if any. Now, just by looking at it, you can tell that if you let a sub n to be equal to 1 over n, then a sub n is certainly bigger than 0, and the limit of a sub n is going to 0 as n goes to infinity, and that the sequence a sub n is decreasing. So the series that you have here converges by the alternating series test. Now, we saw this one before. It's called the harmonic series. The alternating harmonic series. So we know this series converges. But if you instead take the series where you just make everything positive. Now, to make all of this positive means that I have to take the absolute value of this first factor in this product. But if you take negative 1 to the absolute value, you just get 1. You would then have 1 to a power. That's just 1. This would vanish. The only thing left is 1 over n. And we know that series diverges. So, since the series converges, but the series formed by taking the absolute value of the terms diverges, the series, as n goes from 1 to infinity, of negative 1 to the n plus 1, all over 1 over n, that thing converges, but it's considered to converge conditionally. And that's the bad kind of convergence. It means that the order of the terms, the way they're added up, you have to add it up that way, or you might get different answers when you do so. And that's it. That's all we really need to talk about as far as absolute convergence and the absolute convergence test.